Hi, my name is Kat Marchán, and this is my talk, Gotta Go Fast, or How to Make Your Users Think Something Broke. This talk is going to talk mainly in terms of language package managers, but it's relevant to system package managers as well. The point here is to knowledge share, tricks that make users go, wait, did it actually work? As a quick heads up, there's a slide at the end of this talk that involves a lot of motion, so be mindful if you're sensitive to that. I'll give you a quick heads up. So let's get started. Who am I? I am the former NPM CLI architect. That's the package manager for the JavaScript ecosystem. I spent the era of like NPM version 3 to NPM version 6 kind of as like the lead developer at times for most of that. I also spent some time on the NuGet client team. That's the C# package manager. I am currently the maintainer of Origin, which is a JavaScript package manager that's very, very fast and that I'm using to like try out new things that I think would be interesting. I'm also kind of an obsessive speed demon. Like during my NPM era, I managed to speed it up by about 500 times in some scenarios, which is kind of ridiculous, but I swear it happened. And Origin is even faster. So this is what I mean. Like, I really like making graphs that look like this. Origin, by the way, is the one at the bottom there. So before we get started, let's kind of go over the stages of installation so we have some context. So these steps, they vary depending on package manager, they vary depending on ecosystem and your requirements, but most of them are generally going to be there in some way, shape, or form. The first step is resolve. This is the resolver. It's what figures out what dependencies you want in your final graph. The next one is pruning extraneous. This is the process of looking at the files on your file system and saying like, oh, I don't need that file anymore from my previous install because my new graph says I don't need it. You have to remove those. Then you have fetch packages, which is actually downloading packages and getting them from the network and putting them somewhere that you can use them. Extracting data, which is where you actually crack open the package and unpack it and pull all the files out and you put them somewhere. Hopefully you're putting them in the place where your user wants you to put them. Finally, you have a build or compile step. Some package managers might require building or might have scripts or stuff like that. This is where you run that because now you have all the files extracted. Now you can squash all of these together in various ways, but you won't necessarily see perf improvement if each step is operating at system capacity. So for example, extracting to destination as soon as a package got resolved did not actually speed Origin up very much. And it prevented some potential tree optimization. But PnPM, another package manager for JavaScript, claims it helped them a lot. So I'll take them at their word, but that's a difference in experience. So let's talk about what slows you down during package management. These are the core things to watch out for. The first is network I/O. This is by far usually the slowest. You have to be really mindful that not everyone in the world has gigabit internet as well. So keep that in mind. Next up is dependency resolution. It's often I/O bound. So network I/O can affect it too, but for package managers that require one version, one package, one name, one version, this is actually an NP hard problem, and it can get very expensive. You add network I/O to that, and it gets completely untenable. After that, we have syscalls, actual file system calls, file writes, creating directory, reading directories, setting permissions, all that kind of stuff. That's expensive and takes up a surprising amount of time. Decompressing packages is a very CPU heavy operation. You'll actually very easily peg your CPU while doing concurrent extracts if you're doing that, because that's a thing that takes time. It's not just decompression, but validation, anything else that you got to do around that. And finally, doing things that you don't need. If you don't need to do something, then don't do it, right? And what that means for you is kind of up to you. And it's kind of a thing that you can be very creative with. I think this is the most fun part for me, and we'll talk about this more a little later. So what do? You measure. Flame graphs, sorry. So there's different scenarios. You want to split it up into different scenarios. For example, fully cold start, cold cache, warm cache, lock file, no lock file, etc. You want to keep track of these scenarios and have different benchmarks for each of them. And micro benchmarks are not good. They are useless. Do not micro benchmark. Do not try and make up imaginary projects. Use real world projects. If you have trouble finding real world projects, just ask your community. They will tell you, they will give you different kinds of scenarios, different sizes of projects, different interesting things. You can also just search GitHub and find things like that. But I find that cleaned up production manifests are most useful. But whatever you do, don't make up imaginary things. Don't try and find a platonic ideal. Don't try and come up with examples yourself. You're not going to come up with anything useful. Trust me. You're not going to get what you want out of that. Flame graphs are your friend. I'm not going to go into how to use them, but I'm definitely going to tell you to use them. And I'm going to show you a couple just to get the point across. Spikes. Exploratory spikes. Failure is okay. Always test out your ideas and compare. Don't assume an optimization will actually help. Get comfortable with failure. Now, you can actually spend weeks on spikes that come up with nothing, and you have to be okay with that. That's happened to me. That's okay. I learned a lot. You have to learn a lot in order to be in this business, basically. And finally, take notes. I have literally never taken notes. I'm very bad at this. I hope that you are not very bad at this. And I encourage you to take your notes because you'll be a much happier person if you have notes to look back on and go like, oh yeah, this is what I did. Now let's talk dependency graph algorithms. I'm not going to go too deep into this because I'm sure there's plenty of talks in this conference about SAT and ASP and CDCL or whatever that is. I don't usually deal with algorithms like that, but this is an important critical part of your performance profile. Basically, parallelizing network I/O is critical for performant dependency graph algorithms. You are not going to get a fast algorithm if you're doing sequential network metadata fetches as you go along, right? SAT ASP solvers can be very slow. You might have to find some shortcuts so that it's not really a SAT problem. Like you can find ways to do that are dependent on your specific package manager. In an ideal world, you would be able to do off the shelf, but there's not really a lot to pick from. There are some at this conference that claim to do that, and you can try them, but they're going to have their own constraints. They might not be good enough for your use case. And finally, PubGrub. I want to mention PubGrub because it is a very cool algorithm. It's used by Pub, the package manager for Dart, and I believe Bundler also switched over to using it. The important bits about it is that it's an ASP-ish resolver with some shortcuts and some interesting approaches to things to make things a lot faster. And it is very good at error reporting. It is very good at telling your users, this is why I can't resolve this graph. These are the dependencies that are conflicting with each other, and this is why they're conflicting. And they're very human-oriented messages, and that's also very important. That's something to optimize as well. Let's go back to optimization, stuffing the pipe. What I mean by this is making sure that all your resources are getting used at capacity as much as possible. I know, I'm kind of saying the obvious, but you'd figure that like a lot of people would think about this more, but no, you actually have to think about how much CPU am I using at this given point in time. Am I maxing out my CPU? Am I maxing out my local I/O? Am I maxing out my network I/O? How can I balance these out so that I can have the highest throughput? My experience is about 20 to 50 concurrent network apps is ideal. So about 20 to 50 downloads at the same time, and extracting those tends to work really well for me. Test it yourself, whatever works for you. If you know, start the biggest downloads first. If there's a way that you can store that metadata, maybe in your log file, so you can sort things before you extract them, that's very nice, because that way, otherwise you have the potential for like the one big dependency that takes a long time to extract ends up at the end and suddenly takes 10 seconds over what your installation would have otherwise taken. Whereas if you'd started it since the beginning, it would have had time to finish sooner. And, you know, this is the classic example of like what concurrency versus sequential versus serial operation looks like. I'm not going to go too far into this. It's the difference between like go by 1, 2, or 3, or you do all 3 at the same time, or in which case you finish when the slowest one finishes. Cool. Now the real kicker is that async can be worse. Async can literally make things worse. It involves a lot of overhead when you're not spending enough async time waiting compared to the cycles needed for async execution and context switching to do their thing. That said, there's a certain level of concurrency that's still good, but you should treat async with a lot of suspicion if you're trying to optimize your package manager. This is especially true for syscalls, because with syscalls, sync wins, hands down. You want to do synchronous syscalls. You don't want to like try and do like async everything. You don't want to like do async copies, async writes. Don't bother with that. Just do the synchronous writes. It's going to be a lot faster. The vast majority of files are also fairly small, so even if you were doing that, it's not really relevant. It's really just a couple calls. Spreading them across thread per CPU, if you're going to make them concurrent, is optimal. That tends to do a pretty good job because a lot of these syscalls are actually CPU bound. They're not necessarily bound by like this speed. And finally, I want to mention this. Memoizing and caching your make-dir operations is actually very valuable. You'd think that creating a directory would be cheap, but when you're creating thousands of directories and you keep trying to like create the same directory and it fails because that's how like recursive dir creation works, well, that's gonna go awry. So to give you an idea of the impact syscalls can make, let's look at some plane graphs. This is origin, about 69%, nice, of the operating time is just spent with one syscall, which is clone file. Just calling clone file will take up the vast majority of Origin's warm cache install time. 5% on top of that is just creating directories. Everything else is miscellaneous overhead. It's like async execution, logging, progress bar, general quality of life things that I want to do, some verification that I do during extraction, things that I don't really want to let go of. And that's still like only a small part of the runtime compared to syscalls. Now, you can take it even further. This install is about 1.2 seconds, by the way. It's very fast. And these kind of things like pop up at those speeds. But if you want to take it further, you do what Bun does, which is they just make 96.6% of their entire install time is just syscalls. And then you have like a tiny sliver of miscellaneous operations. Now, this is actually about 400 milliseconds faster. It's not that much faster than Origin. And it misses out on a lot of like miscellaneous features, I think. But it is mostly entirely syscalls. This is a package manager. It's doing full package manager things, but it's just interacting with the operating system. So let's move on. Let's talk about content-addressable caching. Typical caches are package name and package version, which is the quick and naive way to do it. It's like our first instinct when we want to make a cache. It's like, oh, we're going to put it by name and by version, and we're just going to throw it in the file system and call it a day. Sometimes you want to have hashes with that. With content-addressable hashes, with content-addressable caching, you save the files to disk by their hash, meaning the file names themselves are the file names themselves are the hash of your files. So where do you store everything otherwise? Well, you can store the addresses in your log file. You can store your addresses in metadata. You can store them in an index file that keeps track of everything. But it makes it a little more complicated, but it has some advantages. So this is what a content addressable cache looks like on disk. You can see the Git-like structure. The file names themselves, again, are the hashes of the files. It's what Git does. File lookup then involves just fetching a desired hash by string name. Now, since you no longer have a name in the cache, you have to figure out other places to store your name and all that stuff, like I said. But that's a resolvable thing. That's solvable. Now, here are some benefits of content addressable hashing. First, you can deduplicate files across versions of packages. If you have the same file across the same 10 versions of a package, you're only going to store that file once because that file never changed. It's kind of questionable how much of a win this is in practice, but it can be pretty significant in the long term. You can validate data on install. So every time that you extract things from the cache, you have the hash available. So you can do a checksum as you extract things. This checksum can actually be pretty cheap, but it's very valuable for local development. You would be surprised at how often users' local caches get corrupted. It happened all the time with NPM because your package manager can crash in the middle of an operation and suddenly you have a miswritten file and stuff like that. If you have file system case sensitivity and source repo issues. So if you have a package with the same name and version that came from one source repository, and then you switch registries and you try and install the same package with the same version and the same name, that might be a different package in that other registry. So now you have a conflict. That is also a bug that used to happen in NPM before we had a content addressable cache. Finally, you can skip basically all the readers that you would need during extraction. So if you have package name version, what you do is you have your directory with your package contents. You replicate the structure of what the package is going to look like, and then extracting from there is just a matter of doing a tree traversal through the file system and copying everything over reading every single directory that's in there, and then copying the contents and all that stuff. You can skip all those reader operations and go straight to the files and take them to the destination from there. So that's fantastic. Another advantage of content addressable storage is in the server. You can do this there too. A lot of client-side benefits apply. Most interestingly, you're able to reduce the overall download data if you host packages at an individual level. So if you, again, the same version of a package is going to have the same file 10 times, even across years. So why duplicate that? If you have server-side storage that is content addressable, you don't have to worry about that. Now, I want to talk about some strategies of the actual installation. So one of those is doing hard links. You can have this cache, you have data in your cache, and you can hard link. You can copy the file. Copying is slow. You don't really want to do copy if you can avoid it. So hard links are one trick that you can use for that. They work by making it so multiple files share the same inode. They're available on basically every file system and operating system. So things to note about hard links. There's no copying needed, so you can extract without having to do a full copy operation. It reduces disk space because you don't have to have copies of the same file over and over. Accidental modification is a risk. This is a negative. So if some operation modifies the file in one place, so you have one project with a build script that modifies one of its files, that's going to corrupt your central cache. So that's a risk that you need to watch out for. Sometimes you may have to do a special copy if you know that a build script is going to happen. And finally, this is slow on macOS. For some definitions of slow, but it's definitely slow on macOS for some reason. So keep that in mind. The solution to hard links is copy on write, which is the new kid in town. It's available on APFS, which is the macOS file system, the newer file system. ReFS, which is what DevDrive uses on Windows 11. XFS, ButterFS, ZFS technically supports it, but it's not available yet for some reason. I think they're working on it, but eventually ZFS will also support it. You can also find references to it as ref linking or cloning or file cloning, not just copy on write. Like hard links, so it's very much like hard links, but data gets copied if it's modified. So if you modify a file, instead of modifying the original data for that file and modifying all the things that are pointing at the same file data, you create a new copy and you modify that copy. To illustrate this looks a lot like our hard link example, right? Forgive me in advance if this is a bit simplified. By the way, if you just know about these systems, I'm just trying to get the point across. So all these three file names point to the same data when the ref links are made, right? And after a file gets modified, the data is written to new blocks instead of the original ones. And then the new file, the modified file points to those new blocks. This is kind of a fundamental feature of the kinds of file systems that support this. Like, they also tend to support cool things like snapshots because of the way they store data, compared to like journaling file systems or whatever NTFS is. I don't know what the hell NTFS is besides bad. Finally, the last section here is just about plain doing less. The fastest algorithm is always O0. So here's some ideas on how to do less in general. Lock files. They're still all the rage, and we love reproducible builds they enable, but that's not everything they do. They let you skip the resolution phase entirely. That's really the most valuable thing for me. You can also put extra metadata in your log files to enable things like validation or file sizes and stuff like that. Just give your package manager clues on how to do operations so it doesn't have to look up metadata every time. And finally, they enable content address based fetching. So you can put your hashes in your log file and look things up that way. Fantastic. What else can we do? What else can we not do, actually? We can optimize the graph. And by that, I mean optimize your graph such that you have fewer dependencies overall. Not that you optimize your algorithm. That works, but we're talking about not having dependencies at all. This might be a little harder with ASP solvers because they're already doing a lot of this work, but for package managers like NPM or Cargo, there is a lot of benefit to, say, finding all the things in our trees that would be duplicated usually and eliminating worst case scenarios. You gotta balance that with calculation costs because this can be expensive, obviously, and it can be its own face. Cool. I also like having the concept of an unsafe mode that you can do. CI environments tend to be really stable. You can skip a lot of validation because CI environments do themselves. And a lot of this validation you need in dev environments because dev environments are chaotic. They break, they corrupt. This is not the case for CI environments. So An example of this is npm-ci, which it's this, if you're unfamiliar, npm-ci is a special npm command that's meant to be used when you have a lock file and no node modules installed. That means like whatever, cold or warm cache, but no node modules. It will skip dependency resolution entirely and skip pruning entirely and just go straight into blasting packages into their destination, trusting that the lock file is correct. So assuming that the lock file worked at some point, it's just gonna install it like that. And this actually makes a big difference for performance. Finally, this is the hard part. Ask yourself if you really need your features. I know that's tough, but ask yourself that question. This comes down to a lot of lateral thinking and creativity. It's also the most fun part of it for me. Like, I could tell you about specific decisions I've made for specific package managers that make things like specific constraints faster, whatever. But in order to do this part right, you have to understand your ecosystem. You have to understand your constraints. You have to understand how far from the expected standard workflow your users are willing to go for the sake of blazing speed. And here's a hint, they are going to go much further than you think. And that's a lesson I've learned the hard way, let me tell you. Like, people are willing to put up with a lot of stuff that doesn't do what they're expecting if it goes a lot faster. And they're willing to compromise a lot more than you'd think. So I give you permission right now to really let yourself go and think outside the box. If you didn't have this one constraint, what could you do? Or more importantly, what could you stop doing entirely? Are you sure people care about it that much? Can you isolate it into a special unsafe mode? You know, that kind of thing. Just have fun with it. And when all else fails, and here's your motion warning, by the way, you can just rewrite it in Rust. I'm mostly kidding. Mostly. Anyway, thank you very much. That's my talk. You can find me on GitHub as Zcat. You can find me on Mastodon and toot.cat Zcat. You can check out Origin at origin.dev. And please show up at PackagingCon community and talk with us. Like, I love talking about this stuff with people, and we have very lively conversations. I hope you all have a great rest of your conference, and I wish I could be there with you, but I am currently sleeping. It's 3 a.m. plus 25 minutes. So y'all have a good one. Bye.